Hey everyone, this is Nadeem and welcome to my YouTube channel. Today in this lecture, we will discuss in more detail about the resonance in RLC series AC circuit. As we discussed in the previous lecture about the RLC series AC circuit, that circuit was consist of the resistor having resistance R, inductor having inductance L, capacitor having capacitance C. In case of the resistor, the current I and voltage VR both are in phase with each other. In case of the inductor, VL is leading the current I by 90 degree, while in case of the capacitor, the current I is leading the voltage VC by 90 degree. So here, if we add these all voltages together by applying the head to tail rule, it will give us such a diagram at higher frequency. At higher frequency, we know that Xc is equal to 1 over 2 phi Fc. So if frequency is high, this frequency in denominator, due to which this Xc will be less. While in that case, at higher frequency, XL is higher. Okay, so here this Xc is directly proportional to Vc. So if this is less, this Vc will be less. If this XL is higher, the value of this VL will be more. Okay, so from here if we add them all together, we will take the magnitude of the VL is more as compared to the magnitude of this VC. So here this VC is in opposite direction to this VL, so we will subtract this VC from this VL and it will give us this point. So here at this point, from this point, we will draw the resultant vector, and we know the resultant will be drawn from the tail of the first vector and will touch the head of the last vector. So this is that resultant vector, and here the resultant is this V. This applied alternating voltage source. So if we add this VR, this VL, and this VC, it will give us this applied voltage. Okay, so the resultant is actually representing that voltage, and here at low frequency, this Xc will be higher, due to which this Vc will be more, and similarly XL will be less and this VL will be more. And here in the vector of this Vc, Vc is the magnitude of the vector of this Vc is more as compared to this VL, and if we subtract this VL, so it will give us this triangle, and we discussed this in a previous lecture in more detail. Here at resonance frequency, this Vc will be equal to VL. This Vc, when equal to this VL, these two vectors will cancel each other, and in this case, this whole RLC series AC circuit will behave as a power resistive circuit, because in power resistive circuit, this VR and the current I both are in phase with each other, and here is that same scenario. So first we will find the magnitude of the voltage of this voltage in case of the higher frequency, and then we will generalize that towards the resonance frequency. So here we have that same voltage, this same diagram as we draw for the higher frequency. So this is that same diagram. Okay, so in this diagram, we have, this is VR, this is VL minus VC, and here this is resultant voltage V. In order to find the magnitude of this, we will apply the Pythagoras theorem. Here, according to Pythagoras theorem, hypotenuse square is equal to base square plus perpendicular square. In this case, this is the base. Okay, this VR is the base, this is the perpendicular, and this is the hypotenuse. So if we put the values here, V square is equal to this base VR square plus the hypotenuse. So here the hypotenuse is VL minus VC. So here this VL minus VC whole square. So instead of this VR, we will put IR, because here the value of VR is IR, the value of VL is IXL, and the value of VC is IXC. So we put that values here. So v square is equal to we take the square on each term, so which is equal to I square R square plus I XL minus I XC whole square. So here we will take the square root on both sides. Here it will be cancelled out, and we take the current I square common from these two, and then if that I square is coming outside from this square root, it will become I, and here this is V is equal to I into square root of R square XL minus XC whole square, and this equation 1 represent as the magnitude of the provided alternating voltage source. Here this V by I is called the resistance as given by the Ohm law. So here this V by I will be equal to impedance, which is represented by Z. So Z is equal to square root of R square XL minus XC whole square. This equation 1 is actually the magnitude for this circuit, the voltage V in this circuit at higher frequency. Okay, so we will generalize that towards the resonance frequency. In case of the resonant frequency, XL will be equal to XC. So due to which that equation 1 will become the square root of so that equation 1 will be V is equal to square root of here we have that I, okay, and square root of R square, and here this XL and XC both are the same, so here it will give us the zero value. Okay, it implies that V is equal to I into square root of R square. Square root of R square is equal to R. So it implies that V is equal to IR. And this is the case of the power resistive, the voltage of the power resistive circuit. Now the equation 2, here the impedance, the total opposition by the RLC circuit at resonant frequency. So at resonance frequency, XL will be equal to XC. So due to which this equation 3 will become this. So here that equation 3 implies that Z is equal to square root of this R square, okay, and here if XL is equal to XC, this value will become 0. So it is equal to 0, and it implies that Z is equal to Z is equal to R, okay, and here this total opposition upper by the RLC circuit will be equal to R. So therefore at resonance frequency, the voltage V is equal to IR, and the resistance in this case is equal to R. So therefore at resonant frequency, the RLC circuit will behave as a power resistive circuit. Okay, so here what will be the current at resonant frequency when the XL is not equal to XC? So it will have some value. Okay, this XL minus XC will have some value, and that will be added with this resistor R. So due to which this is a whole, this resistance will be more. Okay, so if the resistance is high, then the current I in the circuit will be less. Now in case of the resonant frequency, this second term will be 0, and only the this term will be count in resistance. So in this case, in resonance frequency, the impedance or this resistance is less, so therefore the current is more in the circuit when the resonant frequency is achieved in the circuit. So here when this VL is equal to VC, the more current will be flow in the circuit. Now the phase angle at resonance frequency. So the phase angle here is given by tan phi, which is equal to perpendicular by base. Okay, So here in this case, perpendicular is VL minus VC and base is VR. So here VL minus VC, okay, that VL minus VC divided by VR. This VL is equal to IXL minus this VC is equal to IXC divided by VR is equal to IR. This we will take this I as a common here, so it will be equal to I XL minus IXC divided by I into this I will be cancelled, and here in resonant frequency XL minus XC is equal to 0, so it will become equal to 0 divided by the R here, okay, divided by the R, and it is equal to 0, okay. So therefore in this case the angle phi is 0. It give us information that the voltage V and the current I both are in phase with each other. Now what will be the magnitude of the resonant frequency at which the resonance will be occurred? So for the resonant frequency we have the condition is XL is equal to XC, and we know the value of XL, which is equal to omega L, and here it is equal to 1 over omega C, and here this omega is equal to 2 phi f, 2 phi f into L, which is equal to 1 over 2 pi f into C. So if we rearrange them, it will give us this, and if we take the square root here, so it will be equal to f is equal to 1 over 2 pi square root of LC. Okay, this is the relation for the resonant frequency. Now the power factor in this case is equal to the true power, which is power consumed divided by the apparent power, and the true power is equal to VI cos phi and divided by the apparent power, which is equal to VI. Both will cancel each other, and it is equal to the cos phi. Cos phi is equal to the base by hypotenuse. So in this case, base is this VR and hypotenuse is that V. So base is VR and hypotenuse is V. Okay. Now, in case of the here, this is V, and now this V is equal to IR. In case of the resonant frequency, the voltage is given by IR. Okay, so here this VR divided by IR, and here this VR is equal to IR, which is divided by IR, and it is equal to 1. So in case in resonant frequency, the power factor will be 1. So in pure resistive circuit, this current I and voltage V both are in phase with each other, and similarly here this voltage V and the current I is same each and everywhere inside this circuit, and there is no contribution of this L and capacitor C. So because here this VL minus VC is equal to 0, so this whole circuit is behave as a pure resistive circuit. Now the current at resonance frequency will be more. More current will pass from each component of this circuit. Okay, and the phase angle at resonance frequency will be 0, because here this VR and the current I both are in phase with each other, and this is the equation for the resonance frequency, and this is the power factor for the resonance frequency. At resonance frequency to the RLC circuit, the power factor will be equal to 1. So this was some explanation about the resonance in RLC series AC circuit, and that's it, guys. Thanks for watching.